Hi class, this is Blair, and this lecture video we are going to be going through chapter 8, section 4 examples or exercises. This is just your basic complex number calculations. So given that we have complex numbers that are in Cartesian coordinates, how can we find the moduli of these complex numbers as well as the arguments and principal arguments? How can we convert these to polar coordinates or to polar form or even trigonometric form? Recall that we can call that polar or trigonometric form, as well as if we start with a complex number or complex numbers that are in polar form, how can we convert these to Cartesian form as well as identify all of the key features? So let's dive right in. So say we have three complex numbers, z, v, and w, that I have listed above. Let's first actually just talk about what these complex numbers look like. Because a lot of the time when you are converting complex numbers or even identifying a lot of things with complex numbers, you usually can kind of just view them to identify everything rather than calculate them. So let's do that first so that we can kind of get rid of the easy stuff first. Okay, so remember we have a real and imaginary axis. First, let's say that 6 is up here, so that's 6 in the imaginary direction. And that means that z is going to be right there. Okay. Now let's do v. Let's change colors on that one. So let's say that negative 1/2 is right there. We could maybe say that negative square root of 3/2 is over here. Oops. So that means v is right there. And then lastly, w. Let's say w is right here. Okay. Now, let's figure out some things that we'd want to know about these. Okay. So first, this distance from 0 to z is going to be the modulus of z, right? And this angle from this line, from our real axis, over to our imaginary axis, that is going to be our argument plus some 2k pi. Right? So now let's do that. So let's see. We are analyzing z right now, our complex number z. We know just by observation that our modulus is equal to 6. Okay, and we can kind of do a side note as well. We can say that the modulus is equal to the square root of our real component squared. We have 0 real component squared plus our imaginary component squared. So we end up just getting the square root of 36, which is just 6. Okay, so this is the more analytical, mathematical way of doing it, whereas the other way we just kind of knew that it was going to be 6, right? And we have our arguments of z. We are going to be at pi halves plus 2k pi. Okay, Now again, that's by looking at this, but we can also do this mathematically as well, or analytically as well. So we can say tangent of theta is equal to our imaginary over our real. And this ends up being when theta is equal to pi halves plus 2k pi, where we say theta is our argument. Okay, then lastly, our principal argument of our complex number z. Recall, our principal argument needs to be contained on, let's see, that's right. Needs to be contained on this interval from negative pi to pi. So I could not remember whether it included negative pi or whether it included pi, so I needed to look that up real quick. So we want to be on this interval, let's do this. Oh, it's not really working. Okay, let's do this. We want to be on this interval from negative pi to pi. And we say that if we wanted to reach right here, going negatively, we'd have to have negative 3 pi halves, which is going to be larger in magnitude than negative pi. So that would break that rotation. But we could say that pi halves does not break that rotation. So our principal argument of z is going to be equal to pi halves. Okay. Now let's do our other easy one. W. Okay. We know just by looking at it, and I'm not going to do the analytical way as well on this one. I'm going to just be looking at this one. We can say that our modulus of W is going to be 2. It's just the length or the distance from 0 to that complex number is going to be 2. We know our arguments of W are going to be pi plus 2k pi, right? Because we can rotate all the way around from our real axis, from our positive real axis to our negative real axis in order to land that line. Now our principal argument of W. That is where we have to decide whether we choose negative pi or pi, right? Well, we don't include pi in our interval, and so we can't choose pi. Okay, so this means that we actually have to choose negative pi to be our principal argument. Okay. And lastly, complex number v. We're going to end up looking for this to be our modulus. We could have this as our rotation for our argument. And actually, let's choose this as our initial rotation, plus some 2k pi, right, for our arguments. Okay, now with this, we're going to have to approach this one more analytically. So our modulus of our complex number v is going to be the square root of, I need the number, of our row component squared plus our imaginary component squared so this is going to be the square root of 3/4 plus 1/4, which ends up being the square root of 1, which is just 1. Okay, so we know the length of that complex number, or the distance from 0 to that complex number, is going to be 1. Okay, now we know tangent theta is going to be our imaginary, which is negative 1/2, over our real. Okay, now this is going to be true. Let's see. This is equivalent to sine over cosine. Okay, so this is going to be true at, let's see, that is going to be 6/6, 7/6. Plus 2k pi. Which is going to be equal to your arguments of your complex number v. Okay. And lastly, we need our principal argument of our complex number v. And our principal argument of our complex number v, recall, we just have to be in between negative pi to pi. We're just going to referring back up to here every single time. Okay, so we need to be in between negative pi to pi. Well, 7/6 exceeds that pi rotation, so we need to just make sure that we rotate negatively. Or another way that we can think about this too is we can just think, okay, we're going to plug in a -1 for this k. So we're going to take 7/6 minus 2 pi, which is 7/6 minus 12/6, which is just going to be -5/6. So that's just simply this rotation. Okay. Okay, hopefully that all makes sense for complex numbers when we start in Cartesian form. Now let's do a few quick examples in polar form. Okay, so let's do the same thing real quick, where we plot them out just so that we can make the easy simplifications first. So there's our real axis, there's our imaginary axis. Okay, this first one, we extend out by 6, and then we have 0 rotation. So right there, that is our complex number z. Okay, our second one. We extend out by 9. Oh man, I probably should have not have taken that one out so far. 6 is not going to be very far. Let's say 6 is right there. Okay, now let's do V. Say 9, come out right here. And then we want to rotate it around by pi. Okay, now recall cosine plus I sine of some angle is the same thing as CIS of some angle. Okay, so that means that we end up getting that point out here. So that is our complex number V. Okay, now lastly, we'd have extending out by 7, and then we rotate down by negative 3 pi fourths. So that we can say this complex number right here is our W. Okay. Now let's analyze everything. So first with Z, when we're identifying our modulus, we're just simply identifying it from the number itself. So it's just that leading coefficient. So our modulus is 6. Our argument is going to be that angle plus 2k pi. And then our principal argument is just the angle of your arguments that satisfies that negative pi to pi rotation, which is just going to be 0. And then, I almost went ahead, and then we want to convert this into Cartesian coordinates. And I'm going to actually take a step back and hurry and do that up here as well, because we forgot to up here. Okay, so once we have everything identified up here, so say with complex number Z, we've already identified the modulus and we've already identified the argument and principal argument. We just simply need to plug those in, right? Because we know that some complex number, we're going to say this is an arbitrary complex number. We can say that some complex number is just the modulus times CIS of some argument. Okay, so we can simply just follow that. So we can say that this complex number is going to be its modulus, which is going to be 6 times CIS of an argument. Okay, and it can be any argument, it doesn't have to be the principal argument. Okay, now we can do the same thing with W. We can say it's the modulus times CIS of any argument that is a complex number in polar form. And lastly, we would have 1 times CIS of 7 pi 6. Okay, and that would be it for converting to polar form. Okay, now let's come back down here again. Okay, so now just with only looking at this number, this complex number, we can say, well, how many real components do we have and how many imaginary components do we have? Because that's all we're really doing when we're converting it into Cartesian form. We can say that we have 6 real components and no imaginary components. So this would be our complex number in Cartesian form. Okay. Now, let's do this again for V. So again, just from looking at everything, we're going to identify our modulus and argument and such. So our modulus is going to be 9, and our argument is going to be pi plus 2k pi. And then our principal argument, since our principal argument needs to be in between negative pi to pi, where we include negative pi and we do not include pi, this means that our principal argument is going to be negative pi. Okay, now by looking at this number for converting, okay, we can say V, and recall you can do conversion however you want. You can convert by knowing your previous knowledge in this chapter of converting from polar to Cartesian if you'd like. Or you can kind of just look at it like I am doing right now. It does not really matter how you want to go about doing it, okay? But either way, so with this, we can say how many real components do we have? Well, we have negative 9 real components. We're going to the left by 9. And then we have 0 imaginary components. So we're going up or down by 0. That is that for that one. Okay. Now lastly, we have this W. So this W will have a modulus of 7. An argument of negative 3 pi 4 plus 2k pi. And a principal argument of negative 3 pi 4ths, okay, because negative 3 pi 4ths is in that interval. Okay, so that is that on that one. Now, what we need to do is we want to convert this to Cartesian form, okay? Now, we know that this is going to have equal distance going to the left and to the right, right? But then just by a magnitude of 7, right? Because this is going to have a 7 distance. Okay. But we know that that's where we're going to be getting like our square root of 2 over 2, square root of 2 over 2. Okay. So we could actually just kind of logic our way out. We could draw a triangle here where we know that this angle is some 45-degree angle. And we have 7 for our hypotenuse. And we want to know what our A and our B are. Right? And so we can say, okay, well, cosine, or A is going to be equal to seven cosine of 45 degrees, and B is also going to be equal to 7 sine of 45 degrees. Well, sine of 45 degrees and cosine of 45 degrees are equivalent, so we can say that these are equal. Those end up going to be square root of 2 over 2. Well, recall that we're now going to the left and then down. So, but we're just going to be looking at 45 degrees right now. So it's going to be square root of 2 over 2 times 7. So we'll have 7 square roots of 2 over 2. Okay, so that's that distance going this way and this way. But now we just need those negative signs. So we can say W is going to be going to the left in our real direction, 7 square roots of 2 over 2. And then down in our imaginary direction by 7 square roots of 2 over 2. And that is it on that one. Okay. Yeah, and that's pretty much it for this lecture note. These lecture notes. Give me 1 second to quickly look back again and make sure that there is not another way that I want to describe how to do that. There is another way that we can think about this, right? Because if you recall, what we were using for Cartesian and polar conversions is we were using the x is equal to r cosine of theta, y is equal to r sine of theta. So we're using these two for converting from polar to Cartesian. And then we were using x squared plus y squared is equal to r squared, and tangent of theta is equal to y over x for converting from Cartesian to polar. Okay. Now what we're going to be doing is we're just going to be kind of relating it to this left-hand sided guy, right? Because we are going to be converting from polar to Cartesian. Right? So let's make this relation and we can say, well, x is now our a, so we can say a is going to be equal to r cosine of theta, and b is going to be equal to r sine of theta, which is kind of similar to what we did right here, but we don't necessarily need to use that 45 degrees, so that we don't actually need to make this realization of these have to be negative in order for going to the left and down. So we can just simply plug those in and we can say, well, a is going to be equal to 7 cosine of negative 3 pi fourths, and b is going to be 7 sine of negative 3 pi fourths, so that this is going to be negative square roots of 2 over 2, and this is going to be negative square roots of 2 over 2, where we simply just plug it into this form, a plus bi, where w, that complex number w, is going to be equal to that. Okay, so that's just another way of thinking about that so that we can relate this to sections 8.1 and 8.2 that we've already discussed. And that is it for this lecture video. I will see you guys in the next one.